I'm getting a great shot of Bree's head.
Sorry.
Yeah, that's your head.
Max.
Okay. Where's the like and subscribe sign? Dang it, I can't do my intro. Oh, there it is. Okay, there we go.
Good?
Yeah.
Okay. All right, so let's talk about the lab and the 5 diagrams that you should have. So, you should have one of force friction and force normal that should look something like this, okay? Read the instructions. I want you to circle the points so I know what you're using. Draw a line of best fit. Write the points on the graph. Easiest 2 points you'll ever get in this class. Show me how you find the slope, okay? So that's the first diagram. Second diagram should be, this is when you have like the box is being pulled at constant velocity, okay? Emphasize on the word constant velocity. So you've got your gravitational pull, little force normal action, little force applied action, and then a little force friction action, okay? Make sure that you label these, make sure you draw it with a ruler, okay? Do not freehand this. Make sure that I see the scale. Typically, you might let like 2 centimeters equal a Newton, something like that. Otherwise, you get really small values and it's hard to see, okay? So you're gonna have this one, then you're gonna draw this same thing tip to tail. I always start with my gravitational force first, but then you got your like force applied, here's your force normal, there's your force friction, okay? Should end up back to the origin. If things end up back to the origin, what do you know about the velocity? It's constant. Okay, it might be constant to 0, it might be constant at 5 meters per second, you don't know. Okay, you just know that you're gonna have constant velocity. And then with the force table 1, your first diagram is gonna look something like this. There's vector A, vector B, vector C, okay? It's going to look like this, and then you're going to draw that same thing tip to tail. And Honus came up and asked and said, hey, you know, mine doesn't quite meet back to the origin. It might not, okay? Welcome to science. It might be off by a little bit, you know, it might be something like this. Now, if you're way out here, that's a train wreck. Something has gone horribly wrong, okay? But typically, you get pretty close back to that origin. So that's what those 5 diagrams should look like, okay? Anybody have any other questions on this? Logan.
Number 11.
What's number 11?
3 ways to determine force friction.
Okay. Well, look. Look at the beginning of the lab. When you measured the force that it took to drag the block, okay, at a constant velocity, what else were you measuring? What's the only reason you have to apply this force to make this block move? What's the only reason? There's friction, right? So the simplest way is to measure how much force it takes to pull it. There's your frictional force, okay? That's what you did at the beginning of the lab, okay? Now, you also know that mu equals force friction over force normal. So when you get to the bottom of the page, okay, when you get, let me see that for a second. So when you get down here, okay, and you've got this number 7, okay, here's the mass of the car, right, and you got the coefficient of friction. So with this one, you got your force, you can find your force normal, right? So if you know your force normal and you know mu, how can you calculate force friction? Multiply them together, okay? Now, any force can also be written as what? Those are the 3 ways. Okay?
So it's like the 3 same ways, just like different.
No, they're not 3 ways. No, they are no. Because this idea is based on constant velocity, okay? This is knowing the coefficient of friction, and you're just finding the force friction, or knowing the coefficient and your normal. If you use F equals ma, you can't do this because you're creating an acceleration. So they are related, but they are not anywhere really close to each other.
So does one of them involve the U value and then mass and then gravitational acceleration?
Yeah, that's what this is. Yeah. Yeah. Okay, now, on question number 7, where you have the car moving at 10 meters per second. Remember, this whole thing is an absolute value, okay? This is an absolute value. So when you're looking at this and you're finding this force friction, you're just going to get a number, and it's going to be positive. But what you have to do is you have to look at it in the context of the problem and say, does it make sense to make this frictional force negative? Or does it make sense that I'm going to keep it as a positive value? So if your car is moving with a positive velocity, if it's moving with a positive velocity and you hit the brakes, what are you hoping to do?
Making negative force.
Increase your velocity or decrease your velocity?
Decrease it.
Decrease it. You're going to slow down. So what do you know about the sign of velocity and acceleration?
They're opposites.
They have opposite sides. Now look, F equals ma. So if you want to have negative acceleration, what's the value of, what's the sign of the force have to be?
Negative.
Negative. So if you look on number 7, if you were to make a sketch of a velocity time graph, you're starting here at 10 meters per second and you're going to go to 0. So right away, what sign is your acceleration?
Negative.
Negative. Guess what? What's making this thing stop?
The brake.
Friction. So what sign does your frictional force have to be? Negative. So you look at it in the context of the problem and go, oh, I have a positive velocity. I don't think I'm going to stop this car if I apply a positive force to it. Okay? It's not going to happen. It is not going to happen. Let me see. Breathe seriously. Your answer to number 10 would make a horrible GPA. Hopefully none of you have that GPA.
Number 10.
Yeah.
Oh, I'm striving for 5. I'm striving for 5 as a hurricane.
Okay.
5 like the question?
Okay.
Because that's not an idea.
Anything else you want me to go over? Right, speak now, forever hold your peace.
No, I think.
Okay, we're good. All right, go once, go twice, so, Matt, stop the camera for a bit.
We need like a physics theme, like.
Can we get at least 1,500 likes on this video?
Yeah.
Dude, I'm telling you, man, we need to put this on Twitch, dude. Start streaming it. Dude, we could add the effects to the stream from the camera.
Dude, yes, that'd be genius.
I think we're really making you go somewhere. I think we're.
Is that good?
I
like that,
stand
cam. Yeah.
Dude, that's dirty.
Yeah. Okay.
What's his followers called? Welcome to the bird camp.
You just said,
And
yeah.
then like,
Yeah, it's already
like,
going.
let me know below. Like,
It's been recording for a while.
No, only 40
Any
seconds.
questions you guys have?
It's a good 40 seconds.
We'll do a review.
Yeah, you're gonna wanna keep it.
Okay, all right.
You need a Twitter too.
Welcome back, boys!
Can we get at least 1,500 likes on this video?
Just that alone.
You know, now I'm subscribing just because of that.
Okay, that alone.
It got us
Subscribe. Oh, did you not subscribe?
All right,
Big
so,
Semi.
all right. So, one of the classic demonstrations of Newton's third law involves me risking my life to a certain degree. So what's going to happen is that I'm going to lay back there on the bed of nails. Then I'm going to take a concrete block and lay it on my chest. And then I'm going to have McGriddle smash the concrete block with the sledgehammer. Which, in and of itself, people they go, let me get this straight. You lay on a bed of nails and you let a teenager hit you with a hammer.
Dang right.
Yes. And they're going, are you just stupid? And I really can't defend myself on that question. It's like, maybe a little, okay, but it works. No one's ever missed, by the way.
That's what I'm scared of missing. I'm gonna be real honest.
You're scared of missing.
I saw Nick didn't break it his first time.
Oh, yeah, Nick, yeah. Yeah, Reiswig hit it this morning. The first time he didn't hit it hard enough and it didn't break, which actually hurt worse because then you want that
You just
energy
took
to like
more the
dissipate,
impact. Yeah.
and it just stopped and it was like, oh. Okay. But when you look at, so what we're going to do is we're going to view this from the perspective of Newton's 3 laws. Okay. So what's Newton's first law of motion? Law of inertia, which means what?
An object is
Yeah. Mother Nature is lazy. If Mother Nature doesn't, if you don't have a velocity vector, Mother Nature's not going to give you one. But if you have one, Mother Nature doesn't want to change it. Okay? That's the simplest version of the first law. So, I'm laying here, I've got this block laying on top of my chest. Does the block have mass?
Yes.
Yes. Does it have inertia?
Yeah.
Yes, anything with mass has inertia. Okay? Does my body have mass?
Yeah.
Probably more than it should, okay? But it does. So, I've got a block laying on my chest. My body wants to remain at rest. The block wants to remain at rest. So there's a whole bunch of stuff that has velocity vectors that are zero. Okay, that has no velocity vector. So Mother Nature's going, we're just going to chill out until a force acts on it. So we're going to define this system as anything being down as being negative and anything being up as being positive. So here's the first law, okay? I'm at rest, I want to remain at rest. Now, here's where the problem is. When Magritte drops the hammer, right, okay, what does the hammer want to do?
Keep going.
Keep going.
Hammer wants to keep going, right, because it's already in motion. So, I don't want that to happen, okay, because if the hammer does keep going, it's going to go all the way to my chest, which is bad, okay? So it's like, small problem here. Now I want to jump to the third law. Third law says that for every force there is an equal and opposite force. Okay, or every action there's an opposite reaction. Notice it says for every, okay? Not sometimes, okay? Not, well, every once in a while, okay? No, for every action there is an equal and opposite reaction. It isn't just on test days, it isn't on Wednesdays or Tuesdays at 12:08 in a demonstration with a bed of nails and a physics teacher that might get impaled, okay? No, for every force there is an equal and opposite force. For every action there's a reaction. So here's the main part of what I'm banking on. When Magritte hits the block, do I want the sledgehammer to accelerate?
Yes.
Yeah, you want it to stop.
Yeah, I want it to accelerate. Because guess what? If it doesn't accelerate, what's going to happen?
You'll die.
Two birds.
It's going to keep going all the way through to my chest. That's bad. Okay? I want this thing to accelerate. And again, most people, you say that to most people outside of a classroom, you're going, oh, you want to get hit with a sledgehammer and you want it to accelerate. They're going, so you want it to speed up. It's like, no. I want there to be a change in velocity in a small amount of time. That's what I want to have happen. So, what's going to be the sign of the force that Magritte was going to apply to me? What's going to be the sign of that force? Positive or negative? Because, now look, Magritte's coming down, right? Down is going to be defined as negative. So Magritte was actually going to apply a negative force to me. But by Newton's third law, guess what? I have to apply a positive force. Okay? The forces have to be equal and opposite. Okay? That's what has to happen. So here's the deal. So when this whole thing plays out, when you look at Newton's third law, the forces are going to be the same. Okay? He's going to apply a negative force. My body and block is going to apply an upward force that's positive. Okay? So the forces are the same. Now, this is where the math turns into this. So, if it's the same force, which it is because it's Newton's third law, notice this isn't Newton's third suggestion. It isn't Newton's, well, maybe. Okay? No, it's a law. In science, that's important, which means it's invariant. It's a law. So, look at this. I'm laying here. I've got a large mass. I've got a block on top of me that also has mass. So from my perspective, I'm going to have a very large mass, right? So do I want a big acceleration? Me personally. Do I want a big acceleration or do I want a small acceleration? Oh no, I don't want a big acceleration. Big acceleration is going to equal pain. Okay? I don't want my velocity to change very much. Okay? So I want a pretty small acceleration. Okay? Because if I have a big acceleration, call the nurse. Okay? Now, the sledgehammer, though, has a relatively small mass, right? So I want the sledgehammer to have a big acceleration. Okay? That's what I want to have happen. So if you were to look on a velocity time graph, okay, the sledgehammer is going to come down with some negative velocity. As soon as it hits that block, what do I want that velocity time graph to do?
Shoot up upward.
Well, at a minimum, what do I want it to do? Here's 0. What do I want that velocity to do?
Go to 0.
I want that to go to 0 pretty darn fast. Okay? Because if it does this, it's a flat line. For any number of reasons.
Don't worry.
Okay?
CPR certified.
Yo, great!
That
Good.
helped his freaking
You can
ribs.
hit me and stop my heart beating and then revive me. Good. Oh, dear
That would be
Lord.
such a story.
Yeah. Oh, yeah, that would be a good story.
Shattered my physics
Oh,
teacher's
yeah.
ribs, and then I resuscitated him back to
killed my
life.
physics
My
teacher.
student,
Great
yeah,
title for
save
your
his life.
first video too.
Huh?
Great title for your first like YouTube video.
It wouldn't even be
I
clickbait.
story time. I literally died.
Next solar project is put on hold.
It wouldn't think it's straight clickbait.
CEO of Solar Initiative has died. On camera.
Dude, this is no longer YouTube. This is lively.
What do I want the velocity time graph of my chest to be like?
Parodies, shallow line.
Yeah, I'm going to start at 0, and I want a little bit of a blip, and then come back down to 0. Okay? I don't want, okay? Right? So I want this to be relatively small. Right? So this is why you can't look at Newton's 3 laws by itself. Okay? You have to look at them as an entire idea. First law says that, wow, the more mass that you have, the more inertia that you have. The more inertia that you have, the harder it is to get something to move. But once it does start to move, then it's harder to stop it. So it's hard to get my body to accelerate, but if I ever do get it accelerating, then it's going to be difficult to stop it. And that boils down to the second law, which is F equals ma. So if I have the same force and a small mass, I'm going to get a big acceleration. But if I have the same force with large mass, I'm going to have a small acceleration. And then you have Newton's third law that says, hey, for every action there's an equal and opposite reaction. Okay, so let's see if I can survive. So if you want to get your phones and record it, take it.
If I ever make a Tinder, I'm putting it.
Who needs a phone?
If what?
If I ever make a Tinder account, I'm putting this video on there.
Really? Really? That's disturbing.
Oh, it's not funny.
Yeah? Like what? No.
Can we make that a thumbnail though?
It's so many more views.
Physics.
Eli, you should do it like, I think Eli should do like ways on it.
Oh, they're not sharp.
No, not at all.
Are they not?
Oh, they are.
Where's the axe at? They are sharp.
No, they're not. Not for nails.
Yeah, they're sharp. Yes, they're
Touch them. Touch them. Yes, they are. I swear.
Not for a nail.
Dude, just please touch them.
I want that. No, they're not.
Max.
Touch them individually.
Those are sharp.
I
So I
did.
gotta hit the old come down.
Okay.
That'd be
Step
hard.
aside. Step back.
Wait, they should be the thumbnail.
What?
You like on the. Look at him, he's struggling.
I'm old, okay? Back off me, all right? I'm old.
Laughing at.
Just look at that, like that, just. Right there.
That's not terrifying.
Take the block,
Pick it up.
lay it flat this way.
Hold this. This?
Yep. Okay, all right, we good?
Just a little.
No, we're stop. Try to breathe with an elephant standing on your chest.
Like trying to breathe this.
Okay, now.
If you ever get this feeling when there's
Okay.
not a concrete block in your chest, you probably have a heart attack.
Now,
Gosh dang it. Stay out of the
You're not
way.
trying to win the carnival prize in this game.
I know.
Okay, but you can do a good, like, half, three-quarter swim.
Half, 3/4. That's
Yeah.
a lot.
How about half?
Okay.
Yeah, I don't want you to like come running up like Happy Gilmore and a hockey shot, okay? You know, now, don't miss.
Don't miss. That's what I'm scared of. I'm not
Wait,
gonna
what
lie.
side are you using?
The
Don't,
dole.
What are you, what?
what are you thinking?
I thought we were going to get more precise.
Okay, so hopefully here's what happens. He comes down, applies a negative force, the block comes up, applies a positive force, that accelerates, and I have a small acceleration.
Okay.
You ready?
Yes, I'm
I
ready.
will
Are you
flunk
ready?
you off. I really don't get voted.
You know what a guillotine is? Just be like. Guillotine a bird. I feel like he regrets his choices now.
Okay, I do regret this choice. I regret this choice every time I do this. Like, God, what
He
an
is so
idiot.
nervous, he can't.
Okay.
I'm actually pretty nervous too, so it's like.
You ready?
Yeah.
Okay.
You shouldn't be nervous.
Okay, ready?
I'm ready.
It's just a
Oh I know, you gotta hit it hard.
Hard?
Hit it hard, dude. Don't be afraid.
I didn't want to hurt him.
Just give him a love tap.
That actually hits worse because that energy didn't get dissipated, so you drove it all the way down into my chest.
He's like, oh!
Well, I broke it, kind of.
Oh,
crap.
now, this is broken. Okay. Oh. Now I have to build up anticipation again.
That was lame.
All right, let me focus my feng
Okay.
shui. All right. Okay, crouching tiger. We're ready.
Ready?
Yeah.
There we go.
That was broke.
I think it's just too strong of a cement block the first time.
What was that?
I think so.
The third one just.
I didn't know.
Get this off my chest.
Okay, I'm not.
I said chest. Oh.
Do you have another one?
You need some help up.
Do you have another one?
Give him
No.
You should see me chop wood. I'm an animal.
Yeah, okay.
I look like a lumberjack. What do you expect?
Yeah,
No,
no,
like move.
Eric.
In so much pain.
Look at him.
Okay.
Okay. Anyone get a good slow-mo video? Dude,
Oh,
Okay.
okay, wait.
I need to screenshot the video because it's totally worth like a Twitter profile pic.
So one time I did this at a grade school. Oh, I know. It was bad. Because I was wearing a white shirt and then I'd taken a red marker and I'd put like red dots across my back. But then I had a jacket on. So when I got done, I like took the jacket off. And the kids were like, oh, it's red dots, it's okay. I was never invited back.
I'm sorry.
What was that? You know?
It was like in fast mode. Like double fast. Like not
I
just
wanna
fast
step
mode.
on
It was
this
like
one.
so
Seriously,
fast.
Not fast.
Dude, just step on it. It won't.
I've had nails stuck through my
Okay.
shoe before.
Like
It doesn't
extremely
feel
fast.
It will not go through your
It
shoe.
worked.
Can I step on this?
No, actually, you gotta go here.
What's the point of the nail?
Yeah, what's the point of the nail?
What do you mean?
Add dramatic effects. Is that what the nail is for?
Yeah. Now, obviously, I wouldn't do this with like 5 nails.
Yeah, because it's like there's a lot less pressure. So it's like,
Yeah, that would be bad.
Do
Okay,
one thing
so
on
come
that.
over here. All right.
How many nails are in
Right
there?
through the base.
Couple hundred. See, the nails are not going to go through your shoe.
You did it so freaking fast. I wouldn't.
Okay.
I wanna go on this
Here.
side.
This side's better.
This side is better. Then you can see more.
All right, so hold on.
Bro, I have like really good videos of you just like in pain.
Really?
Not even getting hit, just laying there.
Like, this was the fail.
Is that the first one?
You have to watch this. Oh, he's like, ow! You have to swing.
Is this the first one?
Yeah, first one.
Awesome.
Eli, come here.
Yes, wait.
Dude, Nick, I need you to screenshot the picture where I'm just like.
Eli, look how like really you swung this time.
I know, the first time.
The first time was so bad. That's awesome.
How much?
He goes, yeah, it just barely brings it up at all. That hurt Bert a lot.
Well, it did, because
I thought cucumbers weren't allowed in this room.
breaking it.
It's understandable, Bert. Bert, stop.
Haley Jones volunteers for the next time you need to do it.
Huh?
Haley Jones volunteers for the next time you need to do it. She agrees she'll lay on the nail bed.
Yeah, no, we're good. Okay.
Yeah, face down. Yeah, face down. No, I was listening.
No, that's fine.
Yeah.
I want to hear which one? The last one.
Okay. So, time to
Hey, Maddie's scared of balloons, so can we chase Maddie with balloons after this?
Huh?
She's scared of balloons.
I'm scared of balloons too, honestly. It's like,
Okay. So, here's what we've got. Okay. Okay. So, I'm going to let go of the balloon, and what's the balloon going to do? Is it going to accelerate?
Yes.
So why isn't it accelerating now?
Because you're
Force.
No, because
because you're holding it right now.
Okay, so if I tied it off,
It wouldn't go anywhere.
the air can't
there is no.
The air can't
push it. The air can't. It can't push off the air.
Gravity.
Yeah, it can't push off the air, so it won't go forward.
The air is being held in by your
finger.
squeeze.
There is no.
And then if you release.
okay. So here's what we're going to do. We're going to time it. Lonnie, you going to time it?
Yeah.
Okay, you're going to time it. Okay, so we're going to time how long it takes to go from here down to the end.
Here, maybe we better have another
Are you
time.
ready? I'm going to go 3, 2, 1, then I'm going to let go. Okay, you ready?
Now we have two now.
Oh, we have 2.
Oh, we have four.
That's because we don't trust Vaughn.
There's
Okay.
There's 5.
5.
Make it 7.
Okay, all right, here we go. Okay.
Exact time.
I'm gonna go 3, 2, 1, boom. Okay, so ready? 3, 2, 1, go.
Boom.
Well, it's a good thing that I didn't.
Oh my god.
How long did it take?
3.44 seconds is what I got.
Can we do that again?
Yeah, we'll do it again.
That was super. Just a lot of good going. Dude, you think I get myself a haircut with this?
Like, why do you just pull this stuff?
Probably not.
You could try. I would not be against it.
I'm tired. Are you tired?
Okay,
I think you just lays here.
Yeah, that's what they do. I've seen that in like
hold on.
random Facebook videos. And they did that. Like,
Are you gonna use a bed of nails ever again? Or another like?
Okay, now, I'm gonna get, that balloon just tore. Let me go get another one.
okay, let's go.
You're doing great. You don't do your haircut great.
Did you seriously just say that right next to the camera?
About a 99.9.
You're dumb.
Okay. Sean, come here.
No.
One end of the method.
You hit me with that thing, with that bar, and I'm never gonna.
Next on Stanley.
Okay, now we're gonna do this again, but now we're gonna put the shield up there.
Thanks. Now I gotta move.
Now, ideally, I'd use the same balloon each time, because there's gonna be some variance in the balloons. Ideally, I'd use the same one, but we're gonna go try it without this. So now I've got the blast shield here. So the first time took how long?
3 seconds even.
About 3 seconds, okay? So now I'm gonna do it with the shield. Now, ideally, we'd have a control where it was the exact same balloon, but it's not, so we're kinda gonna wing it, okay? So what do you think's gonna happen, the amount of time it's gonna take to go across this time?
It's probably gonna go down.
Quicker, why?
Is there something behind it?
Has,
that the
force has something to
provides?
push off of.
Force has something to push off of. Okay, all right. So, like I said, ideally I would use the same balloon, but it tore, so we'll go with this one. So we'll do the same thing again. Okay, ready? 3, 2, 1, go.
You say go.
You
say
say
go.
1.31.
You kind of-
I got 1.47.
That was a lot faster.
Let's go with 1.47.
Okay, now, here's the reality. The time should have been the exact same. There was a difference in the balloons. This has nothing to do with this. No, I'll show you why. Here, watch out, watch out, watch out. Because look at the mechanism on how it works, okay? So here's the balloon, right? Let's start with scratch. So here's the balloon. Now, start with this idea. What's giving the balloon shape?
The air, the pressure of the air.
But what's the air doing?
It's
Pushing out on the
outside of
elastic.
How is it pushing? But
Gas.
what's physically happening?
It's
Just
deflating.
bouncing
Bouncing
around.
off.
Mary's
It's deflating.
it's deflating. So now, what's air made of? And so help me God, do not say
Oxygen.
air molecules.
Air
Air.
Oxygen.
It's made of a bunch of gases.
Carbon
Nitrogen.
monoxide.
Nitrogen.
Nitrogen. So we got a bunch of Nancy nitrogen molecules, right? And a bunch of Olivia oxygen molecules. Okay? Right? Bouncing around. So they're hitting this and they're changing direction. They're continuously bouncing off. So when I hold this, it doesn't accelerate because of the fact that all of these particles on a net situation are bouncing each other out. Okay? So if you look at Shively holding that balloon, right? The same thing is happening. All of these nitrogen and oxygen molecules are bouncing around inside of that, and it's giving it this uniform shape. So, visualize this. What if I could take Shively's balloon and put it into like liquid nitrogen, where it would get really, 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 really cold? What would happen to the balloon?
Deflate.
It gets smaller, right? Now, you can basically explain all of gas theory with second graders named Timmy in a classroom. So, at normal temperatures, these kids have a certain amount of kinetic energy. And they're bopping around all over the place, and they're hitting the sides of the room, right? And they're all excited, and you're creating pressure on the sides of the room. That's what's happening at room temperature. Now, you take those same kids and you put them in a room that's like minus 100 degrees Fahrenheit, the kids are going to be really, 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 really cold, right? And so they're not going to move us around as much, so there won't be as much pressure, and they won't take up as much volume either. So here's what's happening. Here's this balloon. I was holding the end of it, right? You had all these particles bouncing around. And now, and you all were saying, well, they were hitting off of the shield at the back. So let's just look at one oxygen molecule. So here's Olivia, the oxygen molecule, right? And it's bouncing around, right? So when I let go of this balloon, why doesn't it accelerate upward, up or down? Why does it only accelerate horizontally?
Because the tube thingy that it goes out of is going that way.
Well, are they still hitting the sides of the balloon?
Yes.
But those are bounced out, right? Okay? So if these are balanced, then there's no imbalance in this horizontal direction. So the only way that... Hi?
Can I borrow Logan Varane?
Yes. So, when I let go of the back, do you still have a bunch of particles hitting the front of the balloon?
Yeah.
But you don't have as many hitting the back of the balloon. So you're going to create an imbalanced force that's going to allow that to move forward. Now, if you subscribe to the theory that it's going to bounce off the back, okay? If you subscribe to that theory. So here's Olivia, the oxygen molecule. Olivia, the oxygen molecule, leaves the balloon, okay? Now, as soon as I let go of it, what did that balloon start to do? Which direction did it go?
Forward.
Balloon was going this way, right? So Olivia, the oxygen molecule, has exited the balloon, okay? Much like Elvis. Elvis has left the building. Olivia has left the balloon, okay? The balloon is going this way. So then you say, Well, Olivia, the oxygen molecule, is going to hit the board, and she will. Okay, Olivia will hit this board. I'm not disputing that. But if you say, well, that's going to make the balloon go faster. So what would Olivia have to do to make the balloon go faster?
Go back.
Go back inside.
It would have to hit this and then go bouncing off this and do what?
All the way to the
All the
front.
way to the front.
Yes. And it'd have to hit like the back of the balloon. But what's the balloon doing? Where's the balloon?
Forward.
It's already gone.
It's already
The
forward.
balloon's already gone. Okay? So by Olivia hitting this wall has nothing to do with it because there's no way to transfer that recoil energy back to the balloon because the balloon's already gone. So this shield has nothing to do with it. Okay? There's nothing there because it's going to, the reaction occurs in the front of the balloon. It has nothing to do with what's happening in the back. This is why it accelerates forward because you have an imbalance force because these particles are hitting the front. They're not as many hitting the back. Boom, off we go. Got it? Good? All right. Forward.
Drippy on the ground.
Joey Chadwick.
God, she just wants to
Stanley Birdcam.
like call yourself on.
Dude, get him.
No, I swear to God, you got it.
Haley, you win.
We're all Joyces here. Yeah, that's what I'm saying. Yeah, do you like to laugh?
Okay. Are you finding shapes under pretzels?
Yeah, with making all of our physics things.
Okay. All right. So here's what I want to do. So we've got yonder fan cart, right, which we've shown before. So turn it on, okay? Turn it on, okay? And get it up to speed. What does it begin to do?
Accelerate.
Accelerate. So I want to get an idea of how much force is being provided by the fan blade to make this thing accelerate. I want to get an idea of this force. So what are some things that I can measure to determine the force? Fundamentally, what are the two things I'm going to need?
Mass and acceleration.
Mass and acceleration. So how can I get the mass?
Measure the weight of the object.
Okay, so I happen to have a Newton scale here. Okay. How handy is that, right? So I'm going to zero the Newton scale. And then I'll give this a lift. And we are at 4.20 newtons. So that's the gravitational attraction between the fan cart and the strange rock that we're on. So I got 4.20 newtons. So here's my question. How can I take that 4.20 newtons, which is the weight of the fan cart, so Fg equals 4.20 newtons. Okay, so here's the fan cart, right? Okay. How can I use that to get the mass of the fan cart?
Divided by 9.8.
Divided by what?
9.8, the acceleration of gravity.
Well, what's the acceleration due to gravity?
9.8 meters per second
Yeah,
squared.
this is 9.8, okay? Because here's the deal, if I divide that number by negative 9.8, I'm going to get what? The negative mass, which is just weird, okay? So if I take the 4.20 newtons, right, which is equal to my Fg, which is also equal to mg, and g is my gravitational acceleration. So I can take this, divide it by g, I can get my mass. So somebody take 4.2 newtons and divide that by 9.80 meters per second squared.
0.43.
What'd you get? 0. What?
43.
You beat me.
Exactly?
Well, it's rounded.
14.
No, because I got three significant digits here. I got three
49.
significant digits here.
49.
439,
29.
29. Kilograms. Now, here's how I can check if this is right. If I take this number and multiply it by 9.8, I should get 4.2. Okay? So that's the mass. Now, if I take this fan cart to the moon, what's going to happen to the mass of the fan cart?
It's stay the same. The mass is going to stay the
It's
same.
gonna stay the same
It's going to stay the exact same. Why is my mass going to stay the same?
because it doesn't change.
Why does it stay the same? Because it doesn't
Because
change.
it's the same thing, you're just taking it to a place where it has lower gravitational force.
Bingo. So if you think of this idea of mass being how much stuff is inside, okay? Yeah, it's still the same amount of stuff, right? So if I go to like throw this thing, which I'm not, okay? So it has a certain resistance to velocity because it has a certain amount of mass. If I'm on the moon and I go to throw it, it's going to feel the exact same way in terms of giving it a horizontal acceleration. Now, is it going to be easier to, is it going to feel as heavy on the moon? No, because there's a smaller gravitational field on the moon. And G on the moon is like 1.63, okay? If you go to Mars, it's like 3.5. So it will weigh different, but the mass itself will stay the same. Now, here's the next thing. So how can I take, that's the easy part. So now, how can I determine the acceleration of the car?
Time.
Having a meter stick and the fan cart. Don't want a constant velocity. Why don't I want this thing at a constant velocity? Yeah, there won't be any acceleration, right? I want to multiply mass times acceleration, not mass times the constant velocity. So what could I measure, Logan?
You can measure meters over seconds squared.
How?
If it goes 1 meter,
Yeah,
you time it,
yeah.
and then whatever that time comes out, you square it, and you subtract 1 minus that.
No.
No, divide, I'm sorry. Yeah, because you traveled 1 meter,
Yeah,
that's the meter,
yeah,
over your time squared.
yeah. Molten thought. You're off by a 2. Okay? You'll see why in just a second. So, Logan's right. Can I measure how far it goes? Hold on. Without my glasses on?
Well,
Probably.
like, yeah,
Hold on.
glasses regardless.
Is that big or small?
Small, like glasses for
Yes, that'd be very
We interrupt this important video for a commercial break.
Oh. Max, what are you doing?
Thank you to our sponsor, Coca-Cola.
I didn't get it.
Commercial break.
I didn't get it.
Was it even on it though?
I didn't get it.
What, was that a commercial?
Didn't even get it.
Oh, what we should have done is put the.
Doesn't matter.
ad
Cut it,
for
Mr.
solar.
Burkamp. Cut it.
You
Sorry.
say donate to May Solar.
Okay.
That should be our ad.
Okay. All right. So here's the drill. So we're going to let it go 1 meter. No, stop it.
Oh, we're not stopping it?
I'm gonna stop it. So does somebody have like their clock, their phone?
Yeah, make it like a little bit.
I'm right here.
Okay. All right, you got this. You're gonna time it.
Really?
Sure.
When your phone's on pause,
Okay. Now, turn it on. Now, I want the fan already spinning at full speed when I let go of this. Oh, come on.
Just give me a 3, 2, 1, go.
So we're gonna go 3, 2, 1, go. Ready?
Yeah.
3, 2, 1, go.
Okay.
We killed it.
Oh.
Oh, now it's back to life. Okay. So what do we get for time?
3.15.
3.15? Okay. So, here's the question. And Logan, you're half right, okay? So, we know it traveled exactly 1 meter, true? What else do we know?
Your initial velocity.
We know the initial velocity was what? 0.
The time.
Okay?
We also know
We know
No, fine.
time, which is 3.15 seconds.
We know that
You know, the final velocity has to be positive.
We know the final velocity has to
We
be
could just use
positive.
the d is equal to 1/2 at squared.
Honda says we know distance equals 1/2 at squared plus v naught time.
Yeah.
So what's my initial velocity?
0.
0. So we don't have to worry about this. So you were right, but you forgot the entire formula where there's a 1/2 in there. Okay? So I know how far it went. I know the time. I can figure out the acceleration. True? So if I do 2d over t squared, I can get my acceleration. True? Simple thing. So in this case, somebody take 2 times 1 meter and divide that by 3.15 seconds squared. What do you get? 0.2 what? 0.20 meters per second squared. So now I've got an acceleration, right? Got the acceleration. And I know the mass, so now what can I do?
Multiply the
Find force.
Force. Oh, that's kind of cool, right? So here's the fan, right? Okay, this is going to be important. So the leading edge of the fan was that way. So what are the, at this point, what are the, when I let go of it, what are the 3 forces acting on the cart? So you got gravity pulling down, which was, I'm going to go ahead and make that negative 4.20. And then we got
Force normal.
force normal, which is going to be
positive 4.2.
beautiful. Now, which direction was the force from the fan? To the right or to the left?
left.
Force. Wait, the force? Oh,
Oh wait,
What was
force.
the direction of the force provided
left.
by
to
the
the
fan?
left.
To the
Left.
Yeah.
Okay? Everybody cool with that?
No,
no.
Oh.
Maddie, you're not cool with that.
it goes forward.
Yeah.
So wouldn't the force be going forward?
Well, let me put it this way. Forget that there's a fan blade. If I just said, here's the cart, and I want to push it down to grate, which direction am I going to push it?
Great.
Right? Okay?
But that's when
So-
you were just holding it.
Huh?
You were just holding it. And then,
Okay? Well, if I turn it on,
yeah. Like you were just holding it, so then you have to let go like that.
Oh, did you build that yourself, by the way? Oh.
Get a student.
no, it's just like a kid.
Do we want to record this?
Oh, cool.
Yeah, we do.
No loose connection. Come on. Oh, I have to get a new one for next year. I hate ordering new toys.
We should build
As long as we're having technical difficulties.
that motor
Support the
something
May Solar
by
Initiative.
RC cars.
Yes. Nick.
Okay. Now, when I let go of it, was that any different than me pushing it?
No.
So what direction did the force have to act on the cart?
To the right.
From your perspective, that force had to act which way?
Right.
To the right. Because if the force was acting this way,
Backwards.
yeah. So the force from the fan, so force fan, had to be going this way. If I added all the forces together, would it add up equal to 0?
No.
No.
No. Now, do I have enough information to calculate the force from the fan? Yeah, because I know that's mass times acceleration. So the mass was, what was the mass? 0.429?
1.42.
What was it? No, the mass of the car.
It's on the other side.
0.429.
Yeah, 0.429.
Oh yeah.
Little way. 0.429 kilograms. And the acceleration was what, 0.2? Exactly? meters per second squared. So somebody take 0.429 times 0.2. What'd you get? 0.08?
Yes.
58? Meters, no, newtons, my bad.
Just add a kilogram.
Newtons. Okay? So, good with this?
Yeah.
Now, what would happen if we viewed this from Newton's third law? So what's Newton's third law?
Every
Every action there's an equal and opposite reaction. Every force there's an equal and opposite force, right? So here's my question. How does the fan actually work? What does it do? What's the mechanism of the fan?
It pushes off the air.
It pushes off what?
Air.
So does it push on the air?
Yes.
Yeah.
So by Newton's third law, what does the air have to do?
Push back.
Push back with an equal and opposite force.
wow.
So here's my question.
Science.
If the fan is pushing on the blade with a certain amount of force, and the blade is if the blade is pushing on the air with a certain amount of force, and the air is pushing back with a certain amount of force, how does the fan ever move?
Oh my god.
Oh.
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 This is too
Well,
much
you have
for
friction now. No, that's not even.
That's just going to hurt the cause.
Yeah.
Now, let me give you a quick historical perspective. Keep in mind I teach physics with what I'm about to draw, okay? So, it's the legend of Newton's horse, okay? So this is a horse,
That is quite the horse.
okay?
It does look like a goat.
Back off me. It's a horse. I didn't say it was a good horse, I just said it was a horse.
You know what?
You know what? It might not be a good horse, but it's a great goat. That's its.
Okay. So here's the legends of Newton's horse.
It's definitely.
So you have to understand that in the time of the 1600s, Latin was like the international language of all sciences in Europe, because that was kind of the unifying language. So Newton wrote his work, the Principia, in Latin. So here's how the story goes. After a work is published and everyone's read it and it's all the rage, he goes to hook up his horse. Now his horse, being Newton's horse, is very bright. And he turns around and says, "Whoa there, big boy, back off." He goes, "I've just read your works, the Principia," which is stunning because, number one, the horse can read Latin and translate it into English and speak. It's a smart horse.
Mr. Ed.
So he says, just stop right now. Because here's the story. If you read your third law, and the horse is a horse talking, if I read your third law, if I try and pull on the wagon, what's the wagon going to do?
Pull back.
Pull back.
Pull back with an equal and opposite force, therefore, I can't win. I can't pull the wagon. Let's just call the whole thing off, unhook me, I'm going to go eat grass. How do you argue with the horse?
You slaughter it.
Okay. So
Take it to the glue factory.
this is why I love the political nature of the United States right now. Instead of coming up with a logical argument, beat him.
Nuke
Oh, eat! Oh, horse! Eat the horse!
We build a wall around it and make it pay for
Build a
it.
wall around it, but the horse has to build it itself.
And pay for it.
Yes.
Okay.
True.
Because it's their
All right.
responsibility.
Love that.
So let's take this to a higher platonic level instead of just this base political argument that exists in the United States right now. What's the argument you can give to the horse?
There's less friction on the cart than your feet, so you can pull.
Hold on, there's what?
So the cart is experiencing less friction from the ground than the horse's hooves are. So the force of friction won't balance out the force that the horse is putting on it. So it should move, shouldn't it?
Hold the friction idea. Okay, let's put this in terms of your daily lives. Every day when the bell rings, you all walk out of this room, right? Okay? As painful as it is to leave your physics room, but you still have to go to fourth block. Okay, so,
Honestly, yeah.
yeah, honestly,
I have stats. for
oh,
dogs.
God bless you.
Yeah.
Yeah, what are the odds that that's boring? Okay. So, it's just the nature of stats, okay? Now, here's the deal. You all go to push on that door. What does the door do?
And it
Opens.
No,
Pushes back.
the door pushes back with an equal and opposite force. You all should never be able to get out of this room and open up that door.
Nice.
That's a scary thought for me too.
Seriously,
Trust me.
breaking the laws of gravity.
So, laws of gravity,
Whatever.
I think physics, asparagus. something.
Continue.
Okay. So here's the $1,000,000 question. Let's look at what happens when you all push on the door. Are the only forces involved you pushing on the door?
No.
Mary, what else is happening?
Gravity.
Gravity. Gravity's pulling you down though.
Force normal.
Force normal's pushing you up. So you got that's going this way, but fundamentally, you operating on the door has to be a horizontal situation. Ooh, let's talk about friction. Now, what if I could wave the magic wand and I could make that area right in front of the door perfectly frictionless?
Wouldn't
And you go to push on that door.
We would never stop pushing.
What would you do? When you go to push on the door, what would you do? You'd go backwards.
Forward.
So could you open the door if you were standing on a perfectly frictionless surface? No. It'd be like McGriddle trying to push the blocking sleds out of football practice, right? So if you go to coach and go, Coach, I can't push the blocking sled. If I push on the blocking sled, the blocking sled's just going to push back on me with an equal and opposite force. I can't do this today. I can't physics today, okay? But here's the situation. Leave the horse out of it, okay? Leave the horse out of it. And it goes to something that Max had said earlier. When the horse goes to push on the ground, what's the ground going to do? The ground's going to push back with an equal and opposite force, right? So it's like McGriddle, why do you guys wear cleats? Why do you wear cleats?
Technically, it'd be like increased friction.
Increase friction. So you're increasing the action-reaction force when you push on the ground. So what do you put on the bottom of horses' hooves? Horseshoes. Because that increases the action-reaction forces that occur right here. So when this horse pushes on the ground pushes back. Now the horse is right. Horse pulls on the wagon pulls back with an equal and opposite force. The horse is right. But here's the deal. As long as this set of equal and opposite forces that occur right here are bigger than this set of equal and opposite forces that occur here, you can pull the wagon. So if you could push on the ground, instead of have a set of equal and opposite forces there, that's bigger than the set of equal and opposite forces when you push on the door or when you push on the blocking sled, that allows you to make something move. So the horse is right, but just in that isolated situation. And if the horse was standing on a frictionless surface, the horse would have a valid argument, because the horse wouldn't have the ability to push on the ground and have the ground push back. Okay? Good with this. So what happens when the fan, okay, the fan, there is an action-reaction force with the fan. Okay? Huh?
There's two of them, right?
Yeah. Yeah. And so when that fan is pulling that air, it's pushing off on the air. That's what allows that fan to move down the road. Okay? Got it? Good. Okay, stop that for a second. So on question number 6, because if I don't show you how to do this, you're going to read this question and then want to curl up in the fetal position in the corner and suck your thumb. So we got, if with no friction, force F results in an acceleration A when acting on mass M, then tripling the mass and increasing the force sixfold will result in an acceleration of, okay, and you're going, whoa, no idea what this is even saying. So here's the deal. I want to show you 2 ways that you can solve this problem. One is a very elegant way to do it, and the other one is like a smash mouth physics. Okay? So let's start with the smash mouth physics approach. So what's the basic relationship between force, mass, and acceleration?
F equals MA.
F equals ma. There's the radical concept. All right. So one option is to do smash mouth physics, and you make up numbers. What's the easiest numeric force you can work with?
1.
1. So I'm going to let this be 1 Newton. What's the easiest mass that I can work with? 1 kilogram. What's the easiest acceleration then?
1 meter per second squared.
So this is the basic definition of a Newton. A Newton is the amount of force required to take a 1 kilogram mass and accelerate it at 1 meter per second squared. Now, to give you some perspective, that fan that we just saw, that was accelerating about 2.2 meters per second squared. Okay? So to get a bigger acceleration, that would actually be going relatively quickly if that had an acceleration of 1. Okay? So this is my initial set of conditions. So now, what's going to happen in the new set of conditions? What's going to happen to the mass? So it's going to become 3 kilograms. What's going to happen to the force? So it's going to become 6 newtons. So what has to happen then to balance it out?
Acceleration has to double.
My acceleration has to be
2.
2 meters per second squared. So what happens to my acceleration?
Double.
It doubled. Okay? Now, that's the smash mouth approach. If you like that approach, go with it. Now, here's the more elegant approach, which is actually easier. So you start with the idea that F equals ma. You're going to triple the mass. So instead of m, your mass is going to be what? 3m. And instead of force, it's going to be 6m. So therefore, to balance this thing out, I've got to have
2a.
2a. So this is more elegant, okay? And takes a little bit of insight, but if you like numbers, go with this method, okay? I don't care, but that's how you can handle that. Those are the 2 ways you can approach this. Now, let me give you some hints. When you get to question number 2, how many significant digits are in every number that I gave you on number 2? 3. Every one of these problems has 3 significant digits. Guess what? How many significant digits do you think you should have in every answer?
Probably
3. Now, let's talk about problem number 4. Allocate me that card. So, here's what I want you to think about, and this will make sense when you get to problem number 4. Okay? So, if you go back to the fan cart, the fan cart was capable of producing 0.085 newtons. Call it 0.09. Let's even make it simpler. Let's say it's 0.1. Let's really round it and call it 0.1. So here's my question. The fan itself could produce a force of 0.1 newtons. So, but the cart weighs 4.2. So if I let go of this, producing 0.1 newtons of force, if I let go of it, is the fan producing enough force to make this thing lift up? What would it do? It would accelerate, right? But now, here's the question. Look at this in terms of forces. So if I set this thing on a scale, right? Without the so if I turn this off, the scale would read, if you have a digital scale, the scale would read 4.9 newtons. Because that's what the scale is providing, like the normal force. That's what it's measuring, is the action-reaction. But if I turn on the fan blade, it's going to try and lift it up. Now, it won't be enough to actually lift it up because of the fact that it's less than the weight of the cart itself. But what do you think would happen to the reading on the scale?
Go down by 1.
It's going to go up, down, stay the same.
Down.
It's going to go down a little bit. Why?
Because it's lifting 1 newton of that force.
Yeah, this is applying a little bit of upward force. So, anytime you're not accelerating, what is the sum of all of the forces? 0. So when you get to question number 4, okay, you got a 500 gram mass, okay, you're going to put it on a scale, what should be the reading? Do not make this difficult. Then, I tell you, a helium-filled balloon is tied to the balloon, and the scale now reads 4.8. Okay? So, when you look at this, well, let's start at the beginning. If you have a 0.5 kilogram mass and multiply that by 9.8 meters per second squared, what do you get?
Your new 4 should get.
How about 4.9?
Yeah.
Okay? So a 0.5 kilogram mass weighs 4.90 newtons, right? So think about this. The balloon is providing an upward force. So what's going to happen to the reading on the scale?
It's going to go down.
It's going to go down. And by ever how much it goes down, that's the upward force from the balloon. So when you get to number 4, and even though on D I say draw a free body diagram showing all the forces acting on the mass with the balloon attached, there should be 3 forces on D. The gravitational force, the force in the balloon, and the normal force. All of those forces should add up to 0. Now, when you get to number 5, notice on number 5, I'm telling you it's moving at constant velocity. So therefore, all the forces have to add up to 0. When you get on the back on question 6, 7, 8, and 9, 6, 7, 8, and 9 are nothing more than F equals ma. Number 6 is the easiest question on the entire assignment. Do not make it difficult. I've given you a mass, I've given you an acceleration. Don't overthink it. Now, when you get to 7, 8, and 9, 7, 8, and 9, you're going to do what you did with this cart. You're going to find an acceleration, you're going to find a mass, you're going to multiply those two numbers together. So on 7, 8, and 9, it's just F equals ma. That's it. Okay. I'm done. You're on your own. Not a problem. Where are you going to answer all these questions?
Another page.
Another sheet of paper. Now, on these questions, like some of these questions, you've got to write stuff out. That you can carry your answers all the way across the page if you're writing stuff out. But here's what I want you to be careful of, especially when you get down to like number 5, which has a whole bunch of parts. Make sure that you keep the different parts beside the answers beside those parts. In other words, don't have 5A way up here at the top and expect me to look down here to find the work at 5B. You keep those answers right beside that work. Okay? All right, now I'm done. You're on your own.
Drawing is to draw a vertical line. Is that illegal? Yes, it is.
No, not 1 and 2.
How will the mass and actual change